Okay guys, so now we're going to take a look at lesson 10.6. So there's only 2 lessons left, but as you can see it's starting to really pick up with all of the different theorems compiled together. So this one we're going to break apart. We're going to talk about some chord, tangent, segment theorems, not in relation to the arc measures, but in just relation to the portions of the segments. So here, let's see what that means. So this first one is called what says first here, when 2 chords intersect in the interior of a circle, then each chord is divided into 2 segments called segments of the chord. So that's what they're showing us here with this. So they have 2 segments, 2 chords rather specifically, that intersect inside of a circle. So each of those chords are divided into 2 segments called segments of the chord. So that means AE and EB are a segment of chord AB. And then DE and EC are a segment of chord DC. Now, some of that vocab you're not really going to get too intricate with, but just so if you hear of it, you have some familiarity with what it means. All right, let's talk about the theorem. So if 2 chords do intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So again, if we look at this chord here, AB, then AE is one segment and EB is another segment. If I multiply those 2 lengths together, they're going to equal the lengths if I were to multiply DE times ED. Now that can seem a little bit vague, but let's take a look at just practicing it with numbers, okay? So we look here, find the value of chord ML and then the value of chord JK, that entire length. So what I can do is I can recognize the 2 different chords that I'm working with here. This is one of them, and then this is the other one. Okay, so let's just do the purple one first. So applying what they're saying, they say if I take this portion of that chord times this portion of that chord, so x plus 2 times x plus 1, that's going to equal, if I go ahead and look at my other chord, this portion times that portion. So x times x plus 4. Okay, so now I can go ahead and solve this. This is our algebra work. We're going to FOIL, so x squared plus 3x plus 2 equals x squared plus 4x. If I subtract my x squareds, they just cancel out. So then I have 3x plus 2 equals 4x. I'm going to subtract 3x on both sides, leaving me with 2 equal to x. So that tells me the value of x, but again, they want to know these actual lengths. So I'm going to do it one step further. And I can substitute in 2 for x. So this entire value is 4. This entire value is 3. This is 2. And this is 6. So when they ask me for the length of ML, it's going to be 4 plus 3, which is 7. When they ask me for the length of KJ, it's going to be 2 plus 6, which is 8. Okay, now let's just revisit what we did here because there's a lot going on. So to find those lengths, we use the proportion, the ratio that exists between the segment values. So that's why, even though these 2 numbers, if you're looking at this thinking, wait a minute, I thought they were supposed to equal, the lengths of the chords don't equal. It's the 2 segments of the chords multiplied together that equal the 2 segments of the chord multiplied together. So with that said, let me just erase this because we have a lot on here. Oh, wrong button. There we go. It wasn't registering. Okay, so 2 plus 2, so this, like we said, was 4, and this side is 2 plus 1, 3. So this entire, if I multiply those 2 values, that's a value of 12. This piece here is 2. This is 6. If I multiply 2 times 6, I get 12. So yes, whenever we multiply them, we get the same value. But just to be clear, that doesn't mean the chords themselves are the same lengths. Okay? All right, so let's try another one. I'd like to practice that before we go on. Oh, we don't have any more practice of that. Okay. Well, let's go back a minute. Oh, there are. I thought there were. I was going to say something didn't seem right. Okay, so let's try it with this one here. I'm going to go ahead and multiply x times 3, giving me 3x. And that's going to equal 4 times 6, which is 24. So that one's actually a lot easier to work with. I can solve and get x is equal to 8. They aren't even asking us for the length of the chords. If they were, what I'm going to highlight first would be 8 plus 3, so it would have a value of 11. And then what I'm going to highlight next would be 4 plus 6, obviously 10. So again, the chord lengths themselves are not equal, but using this ratio of this segment times that segment, it should equal that segment times that segment. Okay? All right, let's try the next one. So I can say 2 times x plus 1 is going to equal 3 times 4. All right, so 2x plus 2 equals 12. Subtract 2, 2x equals 10. Divide by 2x equals 5. And that's all they wanted us to figure out, okay? So let's talk about why this works. Just a brief explanation. I found these really nicely laid out proofs. We're not going to work through the whole thing, but they did a good job, and I can explain it this way. So we have these two chords drawn in, like they said. They draw in these extra little segments here, the dotted ones. So if let's just make this so I can write on it. Oops. Okay, if I just write what they're saying. So with these segments drawn in AC and DB or BD. So angle A and angle D are going to be congruent. And that's because, look at this, and this is kind of interesting. If I draw this here, look at the arc that it intercepts. Right here, right? CB. Well, similarly, if I take a look at this inscribed angle, it's intercepting the exact same arc. So that's how I know that angle A and angle D are going to be congruent as they've written here. And the same thing is going to work with angle C and angle B. Plus I have vertical angles. So I have 3 sets of congruent angles, but using our angle-angle similarity theorem, I have 2 similar triangles. And so from there, if I have similar triangles, then the ratio of the side lengths are all proportional. So that's how this works out. The EC over EB is going to be equal in value to AE over DE. And they just have written it a different way. So that's when you cross multiply, you end up getting what it is that we did in that last theorem. So if you didn't like any of that, you can disregard the last 3 minutes. But I just wanted you to understand that there's not just like someone miraculously said, hey, let's make these multiply and have it go from there. So there's purpose behind it, which is pretty interesting. All right, if you are feeling confident and okay, let's continue on. If you're feeling stuck, stop. Go back, rewatch that before we move on, okay? We're going to do a little bit more before we finish this video. Okay, so for now, moving on in our notes, now we're going to take a look at not 2 chords intersecting, but 2 segments or tangents. So here we have a visual. The tangent segment is this segment here that has a tangent to the circle at an endpoint. Okay, and then the secant segment is the one that's a secant. We've already mentioned what those are. Now, the only new term here that they're really emphasizing is this external segment. So that means if we have a secant and part of it falls outside of the circle, then that's called the external segment. Okay, so the whole thing is called our secant segment, or secant would go on forever. That's why it's secant segment. But the portion that falls outside the circle is specifically known as the external segment. Okay, again, some of this vocab isn't going to be super critical for what we're doing at the current time. But we need it so we can understand what the theorem's saying. So if 2 secant segments share the same endpoint outside of a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external. All right, so here's what they're saying. Notice we have 2 secants here, secant segments right here and right here, and they both meet at a common endpoint. So the way we can find the value of these portions, these segments, is to take EA, this piece that's outside, times the entire length, okay? And then we're going to do that with the other one. We're going to do EC times the entire length ED, okay? So let's apply that. Let's find the value of x in this one. So we're going to take the piece that's outside, 9, times the entire length, and the entire length is 20. And we're going to set that equal to this piece that's outside here, 10, times the entire length. So that's 10 plus x. and then we just do our algebra. Okay, so 180 equals 100 plus 10x, subtract 100, we get 80 equals 10x. So x is 8, and that's all they asked us to solve for, okay? From there, we could go ahead and find the lengths of RT or whatever they want, okay? All right, let's try 2 more of these, and then we'll wrap it up by looking at the reasoning. So I'm going to take the piece that's outside, 6, times the entire thing, and if I add these two, I get 15. So 6 times 15, and that's going to equal this piece that's outside, 5, times the entire thing, 5 plus x. Okay, be careful that you make sure to do 5 plus x and not just 5 times x, because that's not the same thing. Okay, all right, so now 6 times 15 we know is 90, and then I distribute, I get 25 plus 5x. 90 minus 25 is going to give us 65, and then when I divide by 5 I get 13. Okay, so x equals 13, and that's as far as they wanted us to take it. All right, now for the last one here, if I'm going to look at this, it's going to be my piece outside, 3 times the entire thing, and that would be 3 plus x plus 2, or in other words, x plus 5. So it's going to be x plus 5. I'm going to set that equal to this piece that's outside, x plus 1, times the entire length. So this entire length here would be, and I'll write it in a different color so we can see it, it would be x plus 1 plus x minus 1. Well, the 1's are going to cancel out, and so we really just get 2x. Okay, that represents the entire length of that secant segment. Distribute, I get 3x plus 15 equals 2x squared plus 2x. Get everything on one side, so 2x squared minus x minus 15 is equal to 0. Okay, and now we haven't done one of these in a while, but we're going to have to go ahead and do a little bit of factoring or quadratic formula. So let's try it out. Okay, so this one, let's see if we can do it. How about 2x plus 5 and minus 3? That multiplies to give us negative 15, and my outer is negative 6. My inner is 5. That gives me a negative 1, so it worked. Okay, so now what I'm doing is I'm going to set each of these equal to 0. So 2x plus 5 equals 0. Subtract 5. 2x equals negative 5. Divide, I get x equals negative 5 over 2. And for the other one, x minus 3 equals 0, so x equals 3. So these are my two answers. And when I look back at my options, if I put negative 5 over 2 in here or in here, actually any of these, I'm going to get a negative distance, and that doesn't work. So it must be x equals 3 as the final. Okay, that one was a little more involved with factoring. Let's just go back to that, taking a look at the explanation so we can see where this one comes from. And if you're good and you don't want it, then you can skip over it. But let's just see what they did here, okay? As to the reasoning as to why this works. It's pretty similar to the other one. They drew in these two dotted lines here, so EB and AD. Again, they're going to share a common arc, so we can use our rules that say that if I highlight this, since this angle and this angle are congruent angles because they have an intercepted arc. So that means that we can go ahead and say that this angle is congruent to this angle. And we can do the same thing. Obviously, C is congruent to itself. So we end up having two congruent angles. So angle-angle similarity theorem says we have two similar triangles, and then again they can make the ratio that says that EC, this length, over AC is going to be proportional to BC, this little piece here, over DC, and when you cross multiply you get the theorem we've been using. So alright, take some time, let that process, we'll see where it stands, and then we'll move on to the rest and just practice some. Okay, thanks guys, great work, bye bye.